Welcome back. This is Module 2, Session 2.1, Learning Paradigms, Supervised versus Unsupervised Learning. And the subtitle on this title card says it exactly right: How Machines Make Sense of the World. In Module 1, we pulled back the curtain on the transformer architecture, tokens, attention heads, and the high-dimensional world of embeddings. You now understand the anatomy of a modern AI system. But today we shift our focus from anatomy to pedagogy. Not what a model is made of, but how it actually learns. Look at the visual on this slide. On the left, you see a perfectly organized grid of red squares and green circles, shapes that have been cleanly labeled and separated. On the right, you see scattered dots on a topographical map, raw, unlabeled points drifting through uncharted terrain. That split captures the entire premise of this session. In the enterprise world, you will hear the terms supervised and unsupervised learning thrown around constantly. But for us, understanding the distinction isn't just an academic exercise. It's the difference between building a model that predicts your quarterly churn rate and one that discovers a customer segment you didn't even know existed. Let's get into it.
This slide is called the learning divide, and it frames the most fundamental question in all of machine learning. Do you have labels? Look at this illustration. On the left side, you see a neatly zoned city, organized blocks, classified areas, labeled data blocks, validated regions. It's structured. It's mapped. A compass sits in the corner because you always know where you are. That is the world of supervised learning, where every data point comes with a ground truth label attached. On the right, it's wilderness, uncharted territory, unlabeled terrain. A telescope sits in the corner because you're an explorer scanning the horizon, not a navigator following a known route. That is the world of unsupervised learning, where you have only raw data and no predetermined answers. The subtitle of this slide tells you everything. The machine learning paradigm you choose depends entirely on one resource: labels. Labels are the dividing line between guided prediction and raw discovery. This is the fork in the road. Every machine learning project you encounter in the enterprise starts here. The single most important question you must answer before writing a single line of code is this: do I have labeled data, and can I afford to get more of it? Your answer determines your entire architecture.
Now, let's zoom in on supervised learning. The subtitle on this slide says it directly: explicit guidance through labeled examples. And here's the four-step feedback loop visualized on screen. Step 1, the input and the correct output are both handed to the model, like giving a student both the map and the destination. Step 2, the model makes a prediction, represented here by a ship's wheel being turned. Step 3, a teacher compares that prediction to the true label and calculates the explicit error, represented by the compass, measuring the gap between where you are and where you should be. Step 4, the model adjusts its internal parameters, gears turning, recalibrating, preparing for the next round. This cycle repeats thousands, sometimes millions of times, and with each iteration, the model's predictions get sharper. The key insight is at the bottom of this slide. The teacher provides both the problem and the solution. The model learns through repeated correction until it reaches high accuracy. Think of it like a student practicing with an answer key. They look at the problem, make a guess, check the back of the book, and correct their reasoning. The word we use for those answers is labels, and the ability to measure your distance from the correct answer at every step. That's what makes supervised learning the most powerful and precise paradigm in the machine learning toolkit.
Supervised learning breaks into two major families of tasks. This slide covers the first one: classification. Look at the machine illustrated here. Raw data, a mix of shapes, squares, circles, triangles, pours into a funnel at the top. The classification matrix inside the machine sorts them, and out the bottom come three distinct bins: spam or not spam on the left, disease or healthy in the center, approved or denied on the right. The goal of classification is exactly what that machine does: draw a definitive boundary between distinct groups and sort every new input into the correct one. The output is always a discrete category, a class, not a number on a spectrum, a label. The enterprise applications here are direct. Email systems use binary classification to separate spam from primary messages. Financial fraud detection is classification. Is this transaction legitimate or not? Medical diagnostics classify patient data as disease positive or healthy. When there are only two possible outcomes, we call it binary classification. When there are three or more, it's multi-class. And there's a third variant worth knowing: multi-label classification, where a single item can belong to multiple categories simultaneously. Think of a corporate document tagged as both legal, procurement, and high priority all at once. For the algorithms, logistic regression is your simple, interpretable starting point. Decision trees create easy-to-follow rules, and support vector machines, SVMs, are the heavy hitters for high-dimensional data, finding the optimal boundary between categories in complex feature spaces.
The second major task of supervised learning is regression, and this slide captures it with a clean, unambiguous visual. A scatter plot of data points with a straight regression line cutting right through the trend. The axes tell the story. On the horizontal axis, house size and location. On the vertical axis, price. The line doesn't sort these points into bins, it predicts a precise dollar value for any new input. That's the defining characteristic of regression. The output is a continuous real number, not a category. The goal stated on this slide: find the relationship between variables to forecast a specific, exact value. Not, is this house expensive or cheap, but what is this house worth? Give me the number. Enterprise applications span every function. Real estate teams use it to forecast property values. Retail operations predict exact sales volumes before inventory decisions. Finance teams forecast future stock prices based on historical trends. And the metrics are different here. In classification, you talk about accuracy, percentage of correct guesses. In regression, you talk about error in the units that matter. Mean squared error tells you the average magnitude of your mistake. R squared tells you how much of the variance in your target variable your model actually explains. You're not asking, were you right or wrong? You're asking, how many dollars or units or degrees were you off by? For more complex, nonlinear business data where a straight line won't cut it, you move to polynomial regression or gradient boosting to capture the curves.
Supervised learning is powerful, but it comes with a price. This slide is called the cost of supervision, and the scale illustration says it all. On the left pan of the scale, you see a target with an arrow in the bullseye. That's the advantage. Models trained with labels have an explicit target to optimize toward. The result is proven, highly interpretable, near human performance. When you need a model that works reliably and whose decisions you can audit, supervised learning delivers. But look at the right pan. It's crushed under the weight of a massive glass tower. That tower represents the bottleneck, data labeling, and the scale is tipped dramatically in its favor. Consider the numbers on this slide. Complex labeling tasks can cost between $1 and $100 per label. A dataset of 10,000 examples could cost you anywhere from $10,000 to $1 million in human annotation time alone. And that's before you factor in the months it takes to get domain experts, doctors, lawyers, financial analysts, to review and validate each record. The third bullet is the one that keeps machine learning engineers up at night: rigidity. Models trained on labeled data perform poorly outside their specific training distribution. If your spam filter was trained on 2022 email patterns, novel phishing tactics from 2025 may slip right through. This is why supervised learning isn't the end of the conversation. It's the beginning of a more nuanced one. The bottleneck of labeling is precisely what motivates the other paradigms we're about to cover.
Now we cross to the other side of the learning divide. This slide introduces unsupervised learning, and the subtitle frames it beautifully: Discovering Hidden Structure in the Wilderness of Raw Data. Look at the diagram. On the left, a dense, undifferentiated cloud of dots labeled raw data. No colors, no categories, no labels. It flows into the model, represented as a precision optical lens, a scientific instrument built to bring hidden patterns into focus. And what comes out the other side? Clustered output. The same dots, now organized into distinct natural groupings, each cluster surrounded by its own boundary. The model didn't need a teacher. It found the structure itself. The paradigm statement at the bottom of this slide captures it perfectly. Like organizing a cluttered closet without instructions, the model detects similarities and creates its own natural groupings without any external hints. This is the power of unsupervised learning. You feed it raw data, customer transactions, network log files, genomic sequences, user behavior patterns, and it surfaces the organization that was already latent in the data, waiting to be discovered. The business implication is enormous. You don't need to know what you're looking for. You don't need to predefine the categories. The algorithm finds the natural fault lines in your data and draws the map for you. That's not just efficient, it's the only way to discover things you didn't know to look for in the first place.
The most common task in unsupervised learning is clustering, and this slide walks through exactly how it works in practice. The three diagrams on the right tell the story. Start with the top panel, a grid of undifferentiated customer data points, all the same color, raw, unsorted, no structure. That's what you start with. The middle panel shows the Voronoi diagram. The algorithm has mapped out regions of influence, assigning each data point to its nearest cluster center. The boundaries are emerging. The bottom panel is the result. The same customers, now cleanly separated into three meaningful groups: high-value customers in red, medium value in yellow, low value in green. The algorithm didn't need a single label to do this. It found those groupings through pure mathematical similarity. The two main algorithms you need to know are k-means and DBS scan. K-means is the classic approach. You specify how many clusters you want, and the algorithm finds the optimal centers. It's fast and efficient, but it assumes your clusters are roughly circular and evenly sized. Real business data rarely cooperates with those assumptions. That's where DBS scan earns its place. DBS scan is density-based. You don't have to tell it how many clusters to find. More importantly, it's brilliant at identifying outliers, data points that don't fit any cluster. In cybersecurity contexts, those outliers are often the first signatures of a network intrusion. In financial fraud detection, they're the anomalous transactions that deserve immediate investigation.
The second major pillar of unsupervised learning is dimensionality reduction. And the visual on this slide is one of the most clarifying images in all of machine learning pedagogy. Look at the top half, a dense, tangled three-dimensional hypercube. Hundreds of nodes connected by a web of lines in every direction. This represents your raw feature space, perhaps 500 columns in a customer dataset, all interacting in complex ways that are impossible for a human to visualize or interpret. It's information overload. Then look at the bottom half. Those same data points flattened onto a clean two-dimensional grid, beautifully separated into three distinct color clusters: red, yellow, and green. The noise is stripped away. The signal is preserved. The structure that was invisible in 500 dimensions is now immediately obvious. That transformation is what dimensionality reduction does. The goal, as stated on this slide, strip away noise and compress features while preserving the most important mathematical information. The technique used here is Principal Component Analysis, or PCA. Think of it as a high-powered executive summarizer for your data. PCA identifies the directions in your feature space that explain the most variance, the principal components, and projects everything onto those axes. The benefit is threefold. It reduces computational cost, it prevents overfitting by eliminating noise, and it makes high-dimensional data visualizable by humans. Enterprise applications include image compression, facial recognition speed optimization, and gene expression analysis in biomedical research. PCA doesn't just save compute, it reveals the hidden geometry of your data.
Unsupervised learning is powerful, but like supervised learning, it comes with its own trade-offs. This slide is the cost of discovery, and the scale visualization makes the tension explicit. On the left pan of the scale, a radial network graph, ordered, precise, mathematical. That's the advantage. Unsupervised learning uses abundant raw data with zero labeling costs. It uncovers hidden patterns that humans didn't know to look for. It scales infinitely. You can feed it millions of unlabeled records at essentially no additional cost. On the right pan, a blurry, amorphous blob of mixed colors, indistinct, interpretively ambiguous. That's the ambiguity. And notice that the right pan is heavier, pulling the scale down. Ambiguity is the dominant challenge. Because there's no teacher, there's no ground truth to evaluate against. You cannot compute accuracy. You cannot run a straightforward validation. You have to ask more uncomfortable questions. Do these clusters make business sense? Are these groupings actionable? Would a domain expert look at this output and say it's meaningful? This slide surfaces two specific risks. First, subjectivity. Interpreting unsupervised results requires deep domain expertise. A cluster of network anomalies might mean a security breach, or it might just mean a batch update ran at 2 a.m. Second, statistical validity versus business relevance. Groups can be mathematically distinct, but practically meaningless. Discovering that your customers cluster into people who bought on Tuesday and people who bought on Wednesday is statistically real, but strategically useless. This is why human judgment remains irreplaceable in the unsupervised workflow.
Now let's put both paradigms side by side. This slide is the diagnostic matrix, your reference table for understanding exactly how supervised and unsupervised learning differ across every critical dimension. Row by row, let's walk through it. Data requirement. Supervised learning needs hundreds to thousands of carefully labeled examples. Unsupervised learning can consume millions of raw, unlabeled records. That's not a minor difference. That's the difference between a dataset that costs $1 million to build versus one you already have sitting in your data warehouse. Primary goal. Supervised learning predicts exact outputs from known inputs. Unsupervised learning finds hidden structure and organic patterns. One is a prediction engine, the other is a discovery engine. Primary tasks. Supervised gives you classification and regression. Unsupervised gives you clustering and dimensionality reduction. Evaluation. This is critical. Supervised learning evaluates with clear, objective metrics. Accuracy, F1 score, mean squared error. These are numbers you can put in a dashboard and defend in a board meeting. Unsupervised evaluation is ambiguous by nature and requires human interpretation and domain expertise to validate. Scalability. Supervised learning is bottlenecked by human labelers. Every new data point you want to train on requires someone to annotate it. Unsupervised learning scales infinitely because unlabeled data is essentially free. Use this matrix as your decision framework. When you're scoping an AI project, scan these 5 rows. The answers will tell you which paradigm fits your situation.
In the real world, you are often positioned somewhere between these two paradigms. This is where semi-supervised learning enters. And this slide calls it exactly what it is, the bridge. Look at the map illustration. On the left, a dense, structured city grid. That's the supervised side, your organized, labeled data. On the right, open wilderness, the vast ocean of unlabeled records. And in the middle, a bridge connecting both worlds. Signals radiate outward from a small cluster of labeled points, red, yellow, and green, propagating their influence across the unlabeled territory like a broadcast tower reaching into the wilderness. The caption at the bottom states the business reality directly. Enterprises often have thousands of labeled examples, but millions of unlabeled records. Semi-supervised learning leverages the massive unlabeled data to dramatically improve the model's accuracy without the cost of manual annotation. That's the practical insight. You've already spent the money to label a small, high-quality seed dataset, but labeling the remaining 99% would cost 100 times more and take years. Semi-supervised learning lets you extract value from the unlabeled majority by using the labeled minority as an anchor. The bridge metaphor is apt. You start in the structured city of supervised certainty, and you use those labeled foundations to extend your reach into the uncharted territory, mapping it, populating it, making it useful without having to manually annotate every point you encounter. The small map guides the exploration of the massive wilderness.
This slide shows the mechanics behind semi-supervised learning, the self-training cycle, and it's one of the most elegant feedback loops in the entire machine learning playbook. The diagram on the right shows 3 phases arranged in a continuous circle. Phase 1 is at the top right. A small pool of labeled data trains the initial model. This is your starting seed, perhaps 100 carefully annotated examples. The model learns what it can from that limited data. Phase 2 is at the bottom right. The model is then unleashed on the massive sea of unlabeled data. It generates predictions for every record it hasn't seen before, thousands of them. Phase 3 is at the bottom left. The model doesn't accept all of those predictions blindly. It only keeps the highest confidence ones, the predictions it's most certain about, above a threshold like 90% confidence. Those high-confidence predictions are permanently routed back into the labeled training pool, expanding it. Then the cycle repeats. The model is now bigger, better trained, and even more capable of making confident predictions on the remaining unlabeled data. The key insight from the left panel: by automatically labeling the most obvious data points, the model effectively teaches itself, multiplying the value of your initial labeled dataset with minimal manual effort. This is compounding intelligence. You start with 100 labels and end up with an effective training set of thousands at a fraction of the annotation cost. The model's own confidence becomes the selection mechanism. It only promotes predictions it's genuinely sure about, preventing garbage from contaminating the training pool.
This slide gives you the operational tool you need to make paradigm decisions in practice, the Paradigm Selection Engine. It's described as your operational blueprint for mapping business problems to AI architectures, and that's exactly what it is. Walk through the flowchart with me. The first question at the top: do you know what you want to predict? If yes, you have a defined target. The left branch takes you to a second question: do you have labels and budget to create them? If yes to both, you land at supervised learning, classification, or regression. You know what you want to predict, and you have the labeled data to train for it. This is your most powerful and direct path. If you know what you want to predict but don't have labels or budget to create them, you land at semi-supervised learning. Use your small labeled seed and scale with the majority unlabeled. Now take the right branch. If you don't know what you want to predict, you're in discovery mode. Second question: do you want to group similar items? If yes, the answer is clustering. You want the algorithm to find the natural segments in your data. If you don't want clustering, but you want to reduce complexity, to compress your feature space and surface the most informative dimensions, the answer is dimensionality reduction. Print this flowchart, memorize it.
When a colleague comes to you with a business problem and asks, what kind of AI should we build? Walk them through these 4 questions. You'll have your architecture decision in under 2 minutes.
Let's bring it all together. This final slide, summary and what's next, doesn't just recap the session. It makes a connection that's critical for understanding how modern large language models actually work. On the left, 3 key takeaways. First, supervised learning is about predicting exact outcomes with a teacher and a map. You know your target, you have labeled examples, and you optimize toward measurable accuracy. Second, unsupervised learning is about exploring the wilderness to find hidden structures. No labels, no teacher, just raw data and a model that surfaces patterns you didn't know to look for. Third, and this is the one that changes how you see every AI system in production today, the LLM connection. Look at the diagram on the right. It shows a large language model as a domed structure sitting on 2 foundation layers. The bottom layer is unsupervised pre-training. That's where the model read the entire internet and learned the statistical structure of human language without a single labeled example. The middle layer is supervised fine-tuning. That's where human feedback was used to teach the model to be helpful, accurate, and aligned with human values. GPT, Gemini, Claude, every major language model you use combines both paradigms. Unsupervised learning builds the foundation. Supervised learning shapes the behavior. Now that you understand how models learn from scratch, the next question is obvious. How do we take a massive LLM that already knows everything and make it an expert in your specific company's domain? That's the world of fine-tuning, and it's exactly where we're headed in session 2.2. See you there.